Hi listeners, welcome to the video lecture series on power electronics. In this video, we are going to understand the fundamental operation of a boost converter with its necessary waveform. Also, we are going to derive the design equations related to the boost converter. For further reading, you can follow this textbook on this corresponding page numbers. The circuit diagram of boost converter is given here. There is a simple modification from the buck converter circuit diagram. Three elements, inductor, switch and diode, are replaced in its positions when compared with the buck diagram. That is the only difference. And in this video, we are going to look into the operation of it, and again we are going to derive all these 14 expressions what were derived in the buck converter. A similar expressions we are going to derive for the boost converter in this video. So first let us understand its operation, and then we will derive all these 14 expressions one by one. The operation of this boost converter can be easily understood by two modes of operation. One is when the switch SW is in on condition, how the circuit will behave. Other one is when the switch SW is in off condition, how the circuit will behave. The green waveform drawn here represents the gate signal given to this switch. So when the switch is in on condition, that is when the gate signal is high, the switch is in on condition, and this on time duration of the switch can also be denoted as dt. T on is equal to dt. This already we are derived in the previous video, where d is the duty cycle of the switch, and off time of the switch is denoted by t off, and it is given as 1 minus d into t. So this two derivations are derived already in my previous videos, and if you sum up this, dt plus 1 minus d into t will give me the total duration of the waveform, which is what we call it as the time period of the waveform, which is denoted by t. And this instant is what we call it as dt, and this instant is what we call it as t, and this duration is what we call it as 1 minus d into t. So now let us apply the gate pulse to this switch and try to see what will happen to this circuit diagram. I have a button here, so let me press this button to make the switch to turn on. So once I turn on the switch, the circuit will behave something like this. If you look at, the inductor is connected directly to the supply, and I turn on the switch, which means that I am short circuiting this path. So once I short circuit this path, this diode will become reverse bias, because this is not going to conduct, because this point is more negative when compared with this point. So automatically this diode will become open circuit. So because of the switch is getting short, this path is becoming short circuited, this diode will become inactive. Now if you look at, the inductor is directly connected to the source. Now the inductor will be storing its energy in its magnetic field. So the inductor now it is in the charging mode. When the switch is on, the inductor is in the charging mode. At the same time, the capacitor, you assume that there is some initial charges in this capacitor. So this capacitor is trying to discharge its energy into the load. So this is the path which now the capacitor is the only source which is connected to the load. So the capacitor energy will be discharging its energy into the load. So during the on time of the switch, the energy is stored in the capacitor. So because of which the current through the inductor, energy is stored in the inductor. So because of which the current through the inductor will slowly increase from its minimum value to maximum value, which is very similar to that of what we discussed in our buck converter. So this is IL minimum and this is IL maximum. So these two currents are the minimum and the maximum value of the inductor currents. Once it has reached, the current has reached its maximum value, I am going to turn off this switch SW now. So once I turn off this switch, now what is happening? The energy which is stored in this inductor when the switch is on, now it is discharging into the load. Now if you look at the energy which is already available in the inductor plus the supply energy, both are discharged into the load. So now the total voltage, this voltage plus the voltage or the energy which is stored in the inductor will be discharging. So since the inductor is discharging, the current through the inductor will slowly come down. Once it has reached its minimum value, Again I am going to turn on my switch S again. So once I turn on the switch again, the inductor current will slowly increase and it will reach its maximum value. Once it has reached its maximum value, again I am going to turn off, which means that inductor current now is in the discharging mode and again it is discharging to its minimum value, and this is going to be repeated for infinite number of cycles as we need it. So when the switch is on, inductor charges. When the switch is off, inductor discharges. When the switch is on, diode is in the reverse biased condition. Only capacitor is supplying the power to the load. When the switch is off, diode is in the on condition and it charges this capacitor from the source and it is going to discharge. The energy from the inductor and the source is discharged into the load. This is what the operation of this buck converter, boost converter. Now let us try to derive the inductor voltage and capacitor current when the switch is in on condition and inductor voltage and capacitor current when the switch is in off condition. So let us try to look into these 2 points in the first part of the derivation. Now the switch is in on condition. We have seen this equivalent circuit already, and now if you look at, this is the positive of the inductor and this is the negative of the inductor, and this, let it be the voltage across the inductor VL. Now if you look at, there is a closed path here and I can see that there will be current circulating into this closed path. Now I am trying to calculate the inductor voltage across the inductor and current through the capacitor when switch SW is in on condition. So this is what I am trying to calculate. So let me try to apply the Kirchhoff's voltage law equation for this loop. If I try to apply the Kirchhoff's voltage law equation for this loop, the current which is circulating inside the loop as of this source is concerned, it is moving from minus to plus. So this comes under potential rise, and if I look at this current through the inductor, it is flowing from plus to minus. So this comes under potential drop. So Vs is equal to VL. And this is, I'm calculating this voltage across the inductor when the switch is in on condition. So I put VL on as equal to Vs and let it be expression number 1. So I calculated the voltage across the inductor when the switch is in on condition. Now I'm going to look into the capacitor current when the switch is in on condition. So to calculate the capacitor current, let me apply the Kirchhoff's current law at this junction. At this junction, if I try to apply the Kirchhoff's current law, I can write this diode is in reverse biased condition when the switch is in on condition. So the current through the diode is equal to 0. So this 0 is equal to IC plus I0. That is, IC is the capacitor current, I0 is the load current. So if I try to apply that, 0 is equal to current through the capacitor plus the load current I0. So from this I can write IC when it is IC is equal to minus I0. So IC I am calculating it when the switch is in on condition. So let me rewrite this expression as IC on is equal to minus I0. So this is the expression number 2 which we are interested in to calculate it. So now 2 expressions. One is VL on is equals to Vs, that is voltage across the inductor when the switch is in on condition is equal to Vs, and current through the capacitor when the switch is in on condition is equal to minus I0. Now we will calculate again these two, VL and IC, when the switch SW is in off condition. So what will happen if I put SW in off? Now if you look at, this is the positive of the capacitor, this is a negative of the capacitor, and this is V0, that is the voltage across the load. Because these two are in parallel, both are similar. You can just remember the expressions what were derived from the previous buck converter. It looks almost similar, only simple modifications are being done. So if you look at now, I want to apply the Kirchhoff's voltage law for this entire loop, because this switch is in off condition. So the current will be flowing in this direction. So for the second part of the derivation, I am trying to calculate VL off and IC off. This is what I am trying to calculate, IC off and VL off. So applying KVL to this entire loop. If you look at this Vs, that is supply voltage, the current is flowing from this blue direction of this blue arrow mark. It is flowing from minus to plus, so it is in potential rise. So Vs is equal to, if you look at the voltage across the inductor, it is flowing from plus to minus, so it is potential drop. And similarly, this voltage across the capacitor, it is also flowing from plus to minus. If you look at the direction of this current, it is flowing from plus to minus, again it is potential drop. So Vs is equal to VL plus V0. So this is the expression I get when I try to apply Kirchhoff's voltage law for this entire loop. So from this, let me try to write the expression for the inductor voltage during the switch S is in off condition. So this becomes Vs minus V0. So this is the expression number 3 which we are interested in. And at the same point of time, now if you look at the diode current is not equal to 0. The diode current is equal to the inductor current because the current through the inductor only it is flowing to the diode. So here diode current is equal to the inductor current IL. So when I try to apply the Kirchhoff's current law expression at this point, KCL at this point, then I will get IL is equal to IC plus I0. IL is equal to IC plus I0. So when I try to find out IC when the switch is in off condition, IC off is equal to IL minus I0. So this is expression number 4. So this is the fourth expression which we are interested in. So let me take all these 4 expressions and write it in the summary sheet here for easy understanding. So the first expression is the voltage across the inductor when it is in on condition is given by Vs. And similarly, I am going to write all these 4 expressions here. The capacitor voltage when it is in off condition, when the switch is in off condition, is given by IL minus I0. So this is the summary of the previous 1 and 2 derivation. Now we have completed these 2 and now we are going to look into the other 2, that is volt second balance of an inductor and current second balance of a capacitor. So I just returned all the 4 expressions what we have derived in the previous 1 and 2, that is the voltage across the inductor when it is in on and off. Similarly, current through the capacitor when it is in on and off. And these 2 expressions are derived already, that is T on is equals to dt and T off is equals to 1 minus d into T. Now, when I try to apply the volt second balance, what it says, VL on into T on plus VL off into T off should be equal to 0. So, I am putting Vs into dt plus VL off, that is Vs minus V0 into 1 minus d into T should be equal to 0. So this is what we call it as volt second balance. So let us simplify this expression. Vs into dt is equal to, plus Vs into dt plus I multiply this inside. So this is become Vs into T minus Vs into dt plus, minus V0 into T plus V0 into dt is equal to 0. I just multiply all these terms. Vs into this T minus V0 into T dt, again Vs into dt and V0 into T. All that I just multiplied inside. Now if you look at here, this Vs into dt and minus Vs into dt will get cancelled. So it is finally left out with Vs into T minus V0 into T plus V0 into dt is equal to 0. So if you look at Vs into T, I can take minus V0 into T as common. So this becomes 1 minus d. 1 minus d. If I take minus V0 into T common from these two, 1 minus d, which is equal to 0. So further simplification of this, Vs into T is equals to V0 into T into 1 minus the duty cycle D, and I can write this D naught is equals to Vs by into T whole divided by T into 1 minus D. So this T and this T will get cancelled out and it is left out with Vs divided by 1 minus D. So this is the expression for the output voltage of a boost converter with respect to its input voltage and its duty cycle D. As already discussed, this duty cycle will always vary from 0 to 1. So when I put D is equals to 0, V naught is equal to Vs. When I put D is equals to 1, if I put, then V naught becomes Vs divided by 1 minus 1 becomes 0. So the denominator becomes 0. So theoretically this V naught becomes infinity. So that is why this converter is called as boost converter, or the other name of this is step up chopper. So this is also called as step up chopper. So this is the next important expression, which I call it as expression number 5. So let me take this expression 5 to the summary sheet and write V naught is equals to Vs. Vs is the supply voltage divided by 1 minus the duty cycle D. So this is the important expression for the boost converter. Now let us go for current second balance. So the current second balance, I am going to multiply current through the capacitor in on condition into its time plus current through the capacitor when it is in off condition into its time. So I minus I naught into dt plus IL minus I naught. IL minus I naught, which is the current through the capacitor when it is in off condition, into 1 minus D into T is equal to 0. So let us simplify this. I will get minus I naught into dt plus IL into T minus IL into dt minus I naught into T plus I naught into dt is equal to 0. So this is the simple simplification of the above equation. So from this expression, this and this will get cancelled out and it is left out with IL into T minus IL into dt minus I naught into T is equal to 0. IL into T, if I take it common out, this becomes 1 minus D. If I take IL into T common from these two, which is equal to I naught into T. So from this, I can write I naught is equals to IL into T into 1 minus D all divided by T. So this T and this T will get cancelled out. Finally, I naught, which is the load current, is equal to the inductor current into 1 minus D. Or I can rewrite this expression as the inductor current average value is equal to the load current divided by 1 minus D. So this is the another important expression which has to be understood very clearly in many of the problems. In the case of buck converter is concerned, this IL average is equal to I naught, whereas here IL average is equal to I naught divided by 1 minus D. If you look at the average value of the inductor current, average value of the inductor current is something in the middle of these two. So this is what I call it as the average value of the inductor current. So this is average value of the inductor current. So this I call it as IL average, and this IL average is equal to I naught whole divided by 1 minus D. So this is the important expression. This is equal to I naught in the case of buck converter, but now it is I naught divided by 1 minus D. It is dependent on the duty cycle, whereas in the buck converter it is independent of the duty cycle. And let it be expression 6, and let me take this expression 6 to the summary sheet and we will write it there. So IL average is equals to I naught whole divided by 1 minus d. This is the next important expression. Next, let us calculate the ripple in the inductor current, that is delta IL. We have already seen in the buck converter delta IL is this part, that is the difference between the maximum value of the inductor current and the minimum value of inductor current, and this is being denoted as delta IL by 2, and again this part is also delta IL by 2. This we have seen already in our buck converter is concerned. So as a fifth part of the derivation, in order to calculate delta IL, this is the common procedure that we can follow. Just you turn on the switch and see that what is the voltage across the inductor when it is in on condition. So we already derived this, that is VL when it is in on condition, we will get VL is equal to Vs. This is the first expression that we have derived. Now this VL can be written as L into di on by dt, di on by dt on, which is equal to Vs. This is, since it is in the on condition, I write it this. Di on is nothing but this part. This part is what we call it as di on, which is equal to delta L. So this can be written as L into delta L, delta IL, that is delta IL all divided by, and this happens, this change in current happens with the time from 0 to dt. So this dt on is nothing but dt, which is equal to Vs. So this is the inductor current ripple. So if I try to calculate this delta IL from this expression, delta IL is equal to Vs into dt whole divided by L. So this can be written as, since t I can write it as 1 by f, this can be written as Vs into d whole divided by L into f or Fl. So this is the expression for the current ripple across the inductor, ripple current in the inductor. So this is the next expression. See, all these expressions, it is not necessary for you to remember. Just understand the procedure. Within 1 or few seconds, you can easily calculate this delta IL. One procedure is, you find out what is the value of inductor when it is in on condition. Simply substitute di on as delta IL and dt on as dt, and finally you will get the expression delta IL, which is equal to Vs into d divided by Lf. So this is expression number 7. So let me take this expression number 7 to the summary board. So expression 7, delta IL is equal to d into Vs whole divided by f into L. So this is the 7th expression, which is of important in nature. So the next part of the derivation is, we are going to calculate the maximum inductor current and the minimum inductor current expression. Let us try to derive these two. So the maximum inductor current, that is ILMAX, I can write it as ILMAX is equal to IL average plus delta IL by 2. So IL average plus delta IL by 2. So this is the expression for maximum value of the inductor current. IL average, we know that it is I0 divided by 1 minus D, where I0 is the load current plus delta IL by 2 is the maximum value of the inductor current. Similarly, the next one is the minimum value of the inductor current, that is IL minimum is given by IL average minus, since it is this is IL average and this is the IL minimum, so minus delta IL by 2, minus delta IL by 2. IL average, we know that it is I0 divided by 1 minus D, which we have derived here. So this becomes I0 divided by 1 minus D minus delta IL by 2, which is equal to IL minimum. So this is the next two expressions, that is, this is expression number 8 and this is expression number 9, which is of importance. So let me take this expression number 8 and 9 to the summary board. IL max is equals to IL average or I naught divided by 1 minus D plus delta IL by 2. And IL minimum is again same expression minus delta IL by 2. With this, let us close the part 1 of our boost converter video, and the remaining derivations we will derive it in the next video. Thank you for your patient listening. Thank you.